So again, as I've said, today our goal is to finish chapter 17, and I think we'll be able to do that with little to no trouble. And basically my main point today is going to be going over some reactions that we've already talked about in previous chapters. These are reactions of alcohols that bear discussion in a chapter on the alcohol functional group. But at the time, I probably said something like, as I'm fond of doing, at the time I probably said, you're not responsible for the mechanism yet. Well, yet is now today, because now we've been through chapter 11 and we can understand these elimination and substitution mechanisms. So for example, I'm talking about reactions such as the conversion of an alcohol, and I'll just be very generic. R can be pretty much whatever we want. But we know that we can convert alcohols. Let me move this chat up here so that I can see it better. We know that we can convert alcohols to alkyl halides, certainly alkyl chlorides, bromides, and even iodides. That's a reaction in chapter 10. So if you need to review that, that's where you can look up that reaction. We also said that we can convert alcohols to the corresponding alkyl sulfonates, such as tosylates. By my count, that's in the first section of chapter 11. I think the book is wrong in its reference here. Certainly double check me, but I think we'll find that in chapter 11. And then we also said that alcohols that have at least one proton in the beta position, meaning on the carbon next door to the one bearing the alcohol group, that these can be dehydrated and give us alkenes of this type. And that was in chapter 8, way back in chapter 8, we talked about that. And so these are reactions we briefly mentioned back then, but we didn't do the mechanisms. Now we can. And again, these are all relevant because these are all reactions of alcohols, and this is a chapter on alcohols. So that's what we're going to spend, I think, most of the class on, is going over those mechanisms. And I hope to convince you that these are now things we can understand. And it's true, we're going to be bringing in reagents with hypervalent sulfur and phosphorus atoms, like, well, phosphorus tribromide isn't hypervalent, but certainly thionyl chloride is, certainly the sulfur in tosyl chloride is. But I think even those we're going to be able to understand as being SN2-like reactions, at least roughly speaking. I think that's the best way to understand them. One could quibble a little bit about that, especially with those sulfur atoms, but I think it's a reasonable way to think of the mechanism that's at least reasonably close to, if not even better than that, to experiment. Good. So for example, we've already said that in terms of converting alcohols to alkyl halides, that you can take a tertiary alcohol, such as this guy here, and you can convert that by using HCl, HBr, or HI to the corresponding alkyl halide. In this case, you would get the tertiary alkyl chloride, looking much like that. And you'd also get a molecule of water. That would be our inorganic side product. But the major organic product will be this alkyl chloride. Or if we used HBr, it'd be an alkyl bromide, HI, and it would be an alkyl iodide. But this is now a mechanism that we can understand pretty well. Of course, the first step, we'd better protonate that oxygen. And there's nothing else that we can use besides HCl. Again, when I look at what I'm given, it's only HCl, and that's the only other thing besides the alcohol. We're using pure HCl, or it would be pure HBr or HI. And so that's going to give us this protonated species. OH2 plus, and now we've converted this oxygen to a good leaving group. Before, it wasn't. OH minus is a terrible leaving group. And in acidic medium, it's impossible for it to act as a leaving group. Remember, in an acidic medium, we don't want to invoke any strongly basic anions. No OH minus, no alkoxide ions, certainly no carbanions, NH2 minus. These things have no place in an acidic medium. They can't exist in an acidic medium. But once we protonate this oxygen, now we've got a good leaving group. And water can certainly act as a leaving group in an acidic medium. And that's going to give us a tertiary carbocation. So again, no surprise that this type of reaction is effective for tertiary alcohols. And then we generate at least one mole equivalent of the halide ion over here. So there's going to be, in this case, chloride ions floating around that will attack our carbocation and give us the alkyl chloride. And this is nothing other than an SN1 reaction. So that's a mechanism we understand quite well now. And so that's, again, this is going to be my main point for today, that we can understand these mechanisms now. They're not particularly heavy lifting. What about what about if we've got a primary or secondary alcohol, though? This works fine for tertiary alcohols, and maybe occasionally secondary, except then you might get a secondary carbocation. Got to watch out for carbocation rearrangements. But what if we had a primary alcohol? And also it holds true for secondary alcohols. But what if we had a primary alcohol? What if we wanted to convert, let's say 1-hexanol, 2, 3, 4, 5, 6, to the corresponding bromide? Well, then of course our reagent of choice would be phosphorus tribromide. We'd certainly want an aprotic solvent. Diethyl ether would be my first choice, since it's relatively easy to get rid of. And as you'll see, we don't even really need to add a base here. And I think there's a very good reason for that. Well, again, phosphorus isn't exactly the same thing as carbon. Not by any stretch. But I think we can think of that first reaction of the alcohol with phosphorus tribromide as being like unto an SN2 reaction. I don't think that does much, if any, violence to the system. And that's going to give us this intermediate with a plus charge and oxygen, and now PBr2, right? Because we've lost one of our bromide ions. So now with this plus charge and oxygen, this whole business is a very good leaving group, just like water is a good leaving group with a plus charge and oxygen. And so now our halide ion, in this case bromide, can come in from behind that, attack the carbon that the oxygen's attached to, and expel that whole thing as the leaving group. And that gives you, in this case, 1-bromohexane directly. And there will be a phosphorus-containing side product. Again, in principle, one could imagine the same thing happening to the other bromines in the phosphorus. Eventually, the phosphorus is going to wind up in a molecule of phosphorus acid, H3PO3, which is, or phosphorus with 3 OHs on it, if you will. And that's going to be water soluble. That'll wind up in the waste jug. But the major organic product will be this one. But here my point is, this is nothing other than an SN2 reaction. If we understand SN2 reactions, we understand that reaction perfectly well. So again, this is my main point today, is that all these reactions were ones that at the time, we kind of had to postpone talking about the mechanisms. But now that we understand substitution, nucleophilic substitution and elimination, we can manage it. So that's going to be relatively straightforward. What about thionyl chloride in order to convert a primary alcohol or secondary alcohol to the corresponding chloride? That I think we'll also see is going to be largely SN2 type reactions. So let me I'll use a different one. How about we use benzyl alcohol? Which again, that horrible name benzyl. Remember, benzyl alcohol is phenyl group CH2OH, right? If we just have the OH in the benzene ring, that's phenol. That's a very different critter. So let's say we wanted to treat this with thionyl chloride. Probably we do this in the presence of pyridine, or you could use triethylamine also, it doesn't really matter. And I would expect that you would get the corresponding chloride, benzyl chloride. plus inorganic side products. One of which, as we'll shortly find out, is SO2 gas. So that's going to be the fate of the sulfur atom in the thionyl chloride. It's going to wind up in SO2 gas. Well, once again, we can put our thionyl chloride over here. And I think the best way to understand this reaction is that it's kind of like SN2. That might be a bit of an oversimplification. There might be some degree to which we form an intermediate by breaking the sulfur oxygen pi bond and then reforming it. You'll see that's what happens when instead of a sulfur here, we've got a carbon there. That's next term, we'll talk about carbonyl chemistry. But sulfur is a different critter from carbon. And I think we're pretty well justified in drawing a step like that. I don't think that's, like I said, being violent to organic chemistry. I think it's okay to show it that way. And we get an intermediate that looks something like this. This is where our base will come in, either pyridine or triethylamine. It's to pull the proton off that intermediate. And the reason we didn't need to do that before with phosphorus tribromide was because we were able to just lose all that as a leaving group and all was well. Here we've got an intriguing looking further reaction though. This is where we generate the SO2. But we're going to, wait, what am I doing? Hold on. We're not ready for elimination reactions yet. So now we can get a true SN2 step. We've got at least one full mole equivalent of the chloride ion that can attack this carbon over here. Instead of just losing the leaving group, those electrons can fold in and form another sulfur oxygen pi bond and then lose a chloride ion. And this will form, if you look at that carefully, that's going to form a molecule of SO2. So that's going to be the fate of the sulfur. And that's very favorable in terms of the Le Chatelier's principle. You're going to lose the sulfur dioxide. That's just a gas that's going to bubble out of the reaction flask. And so, as you know, Le Chatelier's principle says, among other things, that if you can remove a product of the reaction from the reaction vessel, you'll drive the equilibrium forward. And so that's going to be very favorable in terms of driving the reaction forward. We form the SO2, it bubbles out of the flask, hopefully is dealt with in a reasonable way. Hopefully we've got a scrubber on our smokestack or whatever in order to take that out. But be that as it may, that gets us to our chloride. And my main point is really this is just a modified SN2 reaction because we have our nucleophile, the chloride ion attacking, and in some sense the leaving group leaves. So I think that's the best way to understand it. And the first step is kind of like an SN2 reaction. I think we're on pretty solid ground talking about it in that way. And this step, of course, is just a deprotonation. So that's why I'm bringing up these reactions now. We can understand these mechanisms now that we've been through chapter 11. And last but not least in this category, before we get to the elimination, what about forming a tosylate? Like let's say that I'll use a slightly different primary alcohol, and let's say that we treated this with paratoluene sulfonyl chloride. Which looks at first glance a little bit like thionyl chloride, but here we have two S double bond O's instead of just one. Oh, I forgot my lone pair in sulfur. Sin unto me. Anyway, here there's no lone pair in sulfur. Again, we need pyridine or triethylamine or some base. Actually, maybe I'll just go ahead and use triethylamine here, just so you get used to seeing what that looks like. But it's no different, really. If that's the base you're given, then you just use that nitrogen atom and the triethylamine as your base. And here I would expect to get the corresponding tosylate. Looking a little something like this. And there would be inorganic side products also. you would get, in this case, triethylammonium chloride, Et3NH plus Cl minus. We need the base to mop up that HCl for us. So that's what I would expect we would get. And indeed, this one also we can think of mainly in terms of SN2 reactions. So let's put our tosyl chloride over here. And again, sulfur is a very different critter, especially highly oxidized sulfur is a very different critter from carbon, but I don't think it's going to lead you astray if we think about this as kind of like an SN2 reaction. I don't think that's a real significant problem. Yes, everything's different with sulfur being in some strange, that might even be in a strange, what's the word I'm looking for, hybridization. But be that as it may, I don't think that's going to go too badly for us. What am I waiting for here? Got my proton over here, and I've got then 2 CH2s and an isopropyl group. Do I have the right 1, 2, 3, 4, 5? 1, 2, 3, 4, 5. Good. Yeah, I have the right number of carbons here. And on the other side, we've got our toluene group. So I think you'd get that intermediate. And this again is why we would need the triethylamine to pull that proton off for us and get us back to this. So again, I think this is kind of an SN2 reaction, not too different from, so we can understand that, and then just deprotonation. Now, this always gives rise to the following question. There's always a number of sharp-eyed students who say, wait a minute, here when I pulled off the proton with my base, this then underwent another SN2 reaction and gave me the chloride. Why can that not happen here? After all, we've just used our base to deprotonate and we get this thing. Why doesn't something like this happen over here? Everyone understand the nature of the question? It's a very good question. And the answer to the question is that can happen. That's why we need to be very careful when we isolate tosylates. We need to be sure we keep everything very cold, or indeed something rather like that can happen. Now, you won't get SO2 in this case. You'll just get tosylate ion. But that is indeed a very good leaving group, and a nucleophile, even a fairly poor one, such as chloride, could indeed attack here and break that carbon-oxygen bond. So you need to be very careful when you're isolating tosylates. You need to keep those nice and cold. And as long as you do, it's no problem. You can isolate tosylates and mesylates and triflates and things like that, as long as you're careful and keep it cold. Good. But I think this one up here with the thionyl chloride is also different by virtue of us getting SO2 gas out of it. And that once you form that, it bubbles out of solution and is gone. So that's going to make that type of SN2 reaction very much more favorable. Still, in fact, I don't think you can stop that from happening. Good, so much for these ones that are essentially nucleophilic substitution reactions. These are mechanisms that we can understand now. They're all going to be SN2 or SN1 reactions, depending on the structure of the starting material. Good, any questions on any of those? The second one, I don't think there are any SN1s here, because it's happening all in one step. Right, so I think these are all, even the reactions with sulfur, I think we're okay. We're on solid ground thinking of them as SN2. Now, the other one was SN1 because that was a tertiary alcohol. Yep. Good, other questions? All right, well, let's deal with these elimination reactions then. Now, one way of performing an elimination reaction in an alcohol that works especially well for tertiary alcohols, maybe secondary, is just acid-catalyzed dehydration. Again, at the time that we introduced this reaction, we couldn't really discuss the mechanism. But now that we understand elimination reactions, it's no problem. And normally this is done by heating up the alcohol in the presence of fairly concentrated aqueous acid. So this might be concentrated aqueous sulfuric acid, let's say. That's the most common. I think you could also use concentrated phosphoric acid. And in this case, we would expect Zaitsev's rule to apply. And so I'd expect that our major product would be by far this alkene, not this one. You probably will get a little of this, but I would be shocked if it was more than 1 or 2%. It might not even be enough to detect it in the product mixture. The major product will be this one. Or, of course, you could draw that pi bond to the left of the methyl group also. It's the same compound. But that would be the major compound. But now that we understand about elimination reactions, this is no trouble at all for us to understand. The first step will involve, as is so often the case in acidic medium, the oxygen in the alcohol picking up a proton from hydronium. And so you'll get this intermediate. And then just like before, the water molecule can leave, and you'll get this tertiary carbocation. Only thing is, there's not really any good nucleophile left, not even any halide ions sitting around, really. If a water molecule were to attack that carbocation, you just go back to the starting material. But another thing that you can do is deprotonate from the carbon next door to the one bearing the plus charge. We've seen that before. And indeed, that's nothing other than an E1 reaction. So that's a mechanism we're familiar with now. So no big mystery there. That reaction literally is an E1 reaction. We do have to be careful, though, because this goes through a carbocation intermediate. So if one were to do this on a secondary alcohol, especially if I were rather evil with the secondary alcohol I picked, maybe something like, oh, I don't know, that. And if you heated this in the presence of concentrated sulfuric acid, and they could also say H2O, H2SO4, same thing. But if you did the same thing with that, I hope that you guys can convince yourselves that you'll get a rearrangement, and you'll get a product that looks something like that, as opposed to that. So that would be something good for you guys to work out on your own. You'll still get an E1 elimination, but it will go with a carbocation rearrangement. And I think you'll be able to convince yourselves that that's going to be the major product, this tetra-substituted alkene, as opposed to this one, which is only tri-substituted. So that would be, that would not be a waste of time for you to practice that on your own. And as always, if you take a look at that problem and you're not sure whether you're doing it right and you want to bring it to office hours and show me, please don't hesitate. I'll be glad to take a look at it for you. So that's fine, but what if we have a primary alcohol? If we have a primary alcohol, primary alcohols don't want to undergo an E1 reaction. They want to react by an E2 reaction. And so that's why we have other dehydrating agents like phosphorus oxychloride. So let's say, for instance, that we started with our friend 1-hexanol again. And let's say that we wanted to turn it into 1-hexene. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Yep, just checking. Then we've got these powerful dehydrating agents such as phosphorus oxychloride. That's going to be our reagent of choice here. And again, you want to use either pyridine or triethylamine, doesn't really matter. There's other amines besides those, of course, that will also work. You can use ethyl diisopropylamine, and there's plenty of others. You can use diaza bicycloundecane. There's all sorts of these things. But in any case, now we're not going to be able to have this undergo an SN1 or an E1 reaction. These like to react by an E2 mechanism. But again, even still, I think we're on reasonably solid ground, even with this being a hypervalent phosphorus. I think we're on reasonably solid ground, thinking of the first step of the alcohol with this phosphorus oxychloride as being SN2-like. I think that's perfectly fine, given the hybridization of the phosphorus there. And I think we've got 10 electrons here, 2, 4, 6, 8, 10. That's right. So again, with 10 electrons around it, it cannot possibly be exactly like, oh, am I casting spells? Did I do my SN2 spell here? Well, in any case, as you'll see, we'll get an intermediate looking something like this. And, oh, I'm sorry, plus charge and oxygen over here. And so, now is where our pyridine comes in. And again, just like before, we don't really even need to deprotonate that, that oxygen. Instead, we want to deprotonate next door to the carbon with the leaving group on it. And we can use our pyridine for that, or if we had used triethylamine, if we'd used the triethylamine spell instead of the pyridine spell, same result. That can deprotonate on the beta proton, meaning the one that's next to the one that is the leaving group. The electrons in the carbon-hydrogen bond fold in, and we lose this whole business. And again, I think you can see this could in principle happen to the other two chlorines as well. You're going to wind up with a molecule of phosphoric acid. So that's the fate of the phosphorus. Of course, that's water soluble. That's going to wind up in the waste jug. So let me go over all these arrows again. This is showing the lone pair in the base nitrogen pulling off this proton. And again, you want to use a proton not on the carbon that has the leaving group on it, but the one next door to that. That's what we covered in chapter 11. And then you break that carbon-hydrogen bond, you put the electrons in between those two carbons to make a pi bond and kick out the leaving group. All of that will happen at the same time. And so again, you have essentially nothing other than an E2 reaction, because all of this happens at the same time, pulling off the proton, forming the pi bond, and kicking out the leaving group. That happens all at the same time. That falls under the definition of E2 reactions that we gave back in chapter 11. So, by the way, phosphorus oxychloride can also be used with tertiary and secondary and tertiary alcohols. You don't have to use it on only on primary alcohols. Now, the thing is with primary alcohols, if we want to dehydrate them, really we have no choice except to use a reagent like phosphorus oxychloride. Acid catalyzed dehydration doesn't generally work very well because these guys don't want to go through an E1 reaction. They want to go through an E2 reaction. But you can certainly use phosphorus oxychloride with a secondary or tertiary alcohol. The nice thing is if you were to do this with a secondary alcohol, then you don't have to worry about carbocation rearrangements. And the way you know that is as you look through the mechanism, I don't see any carbocations. So actually that means, I didn't think of this in the other class, but if we go back to this secondary alcohol and we treated this with phosphorus oxychloride and either pyridine or triethylamine, well, then it would not rearrange, and we would indeed get that other alkene looking something like that. I guess you could have either E or Z there. I bet this is going to be the preferred one, because I think it would rather have the two methyl group cis than a methyl group cis with an isopropyl. So I bet that's the major product. That'd be my guess anyway. So you actually could get that to go without the rearrangement. My point being, you can use phosphorus oxychloride with secondary and tertiary alcohols also. With those, you have a choice. You can do either acid catalyzed hydration, just taking care to remember that you might have to watch out for carbocation rearrangements. Phosphorus oxychloride is the only dehydration choice for primary alcohols, though, because primary alcohols don't want to undergo E1 reactions. They want to undergo an E2 reaction. But you can certainly use phosphorus oxychloride with secondary and tertiary alcohols also. And I think that's basically it. We just have one other topic for today, which is talking about oxidation of alcohols. So any question on these dehydrations, though, before we do that? All right. Well, what about oxidation of alcohols? I think that's going to be something we talk about a little bit more next term also, as we get into carbonyl compounds in earnest. Now, I just want to double check, because I confess I'm sort of confusing this class with 222 sometimes. I don't believe we've talked about PCC, pyridinium chlorochromate, as a mild oxidizing agent. Oh, I know why, because your textbook uses this other weird reagent. Yeah, we're going to get to that next term. So we'll worry about PCC and equivalent compounds to that next time. What we are going to talk about, though, is the idea of oxidation of alcohols. At least we'll introduce the idea now. We'll have more detail to add to that next term. Oxidation of alcohols. And we'll start with the easiest case, tertiary alcohols. Oops. Like this one. And remember, I know we introduced this, that O in square brackets means generically an oxidizing agent. We're not specifying a particular reagent. In any case, that's the easiest case, no reaction. Tertiary alcohols cannot be oxidized. And I think you'll see there's no way to make C double bond O there without giving 3 bonds to carbon, 5 bonds to carbon. So that's off the table. What about secondary alcohols? Those can be oxidized. And the product in that case is always going to be, I think we'll find, a ketone. And so as an example of this type of reaction, if we were to take cyclohexanol and treat this with a goodly oxidizing agent, chromium 6 oxide is one of them. Usually that's done in acidic conditions, aqueous acid and acetone as our solvent. Now, how do I know that acetone is a good choice of solvent? Because acetone is not going to react with the chromium 6 oxide. It's already as fully oxidized as it can get. Right? You can't oxidize acetone any further. So that's why it's a good choice of solvent. But it's usually done with aqueous acid and acetone, and I would expect we'd get pretty good yield of cyclohexanone. And so our the chromium 6 here is our major reagent. That's our oxidizing agent. I'll just let you know, you might also see this set of reagents written as H2CrO4. And it's the same thing. Chromium trioxide is just the acid anhydride of chromic acid. And I think you can see that for yourself. If you add H2O to CrO3, you get H2CrO4, right? So you might see it written that way as well, in like OWL or something like that. Just so you're aware of it when you see that these two are the same animal. So secondary alcohols, the only possible oxidation product is a ketone. What about primary alcohols? They can be oxidized too. And under these conditions, you will get at first the aldehyde, which will then react further to give you the corresponding carboxylic acid. And so as an example of this type of reaction, let's take O-benzyl alcohol again. And if you were to treat this with chromium 6 oxide in aqueous acid and acetone, you would at first get benzaldehyde, but eventually the benzaldehyde will also oxidize all the way up to the carboxylic acid. So I would expect you to get benzoic acid as the product. Now, are there milder oxidizing agents that will oxidize a primary alcohol to an aldehyde and no further? It'll then stop. And the answer is yes. PCC was always one of them that classically we'd mention in organic text, stands for pyridinium chlorochromate. Next semester, I remember now, your book has this weird reagent called des-Martin periodinane, and we'll introduce that next term. So we're not talking about that yet. That's not part of chapter 17's material. But we'll later learn that you can use a milder oxidizing agent to oxidize a primary alcohol to an aldehyde. For now, it's enough to point out that if you use a really strong oxidizing agent like chromium 6 oxide or the permanganate ion, these things are the strongest oxidizing agents known to man. And so that will oxidize a primary alcohol all the way up to a carboxylic acid. And with that, I'm out of time, and I think that's a good place to stop today. And we're also through chapter 17 with that. Good. So have a great day. Please pick up your exam if you haven't already, and I will see you all on Friday.